Our bisection square root code works beautifully for big numbers. Then we ask it for the square root of 0.5 and it never stops. No answer, no crash, just a loop running forever. The fix is one tiny change to where the search begins and ends. Here is the code we wrote. We set low to 0, high to x, and loop while our guess squared is more than epsilon away from x. Each pass moves low or high and recomputes the guess. For a number like 54,000, it finishes in about 30 steps. But run it with x set to 0.5 and it spins. It should have answered by now, so we stop it. When you hit an infinite loop, reach for print statements and put them inside the loop where the action is. We add one line that prints low, high, and the guess on every pass. Now we can watch what the loop actually does instead of guessing. Run it again, and the screen fills with numbers, scrolling past faster than we can read. And here is the tell. The output is the same three values, repeated over and over, low, high, and the guess never change. The loop is alive, executing every line, but it is frozen in place. A normal search would show the numbers tightening towards the answer. This one is stuck, reassigning the very same guess to itself, pass after pass. Why does this happen only below 1? Our search lives on a number line from 0 to x. For a number bigger than 1, the square root sits inside that range. So the answer is somewhere we are looking. But for x between 0 and 1, the square root is bigger than x, not smaller. The square root of 0.5 is about 0.71, which lies above 0.5. The answer is outside our interval entirely. Watch the interval collapse. We start with low at 0 and high at 0.5. The first guess is the midpoint, 0.25. Its square is 0.0625, far below 0.5, so the guess is too low, and the low climbs to 0.25. The next guess is 0.375. Its square is about 0.14, still too low, so low climbs again. Pass after pass, low marches up, while high stays pinned at 0.5. Because the true answer lies above 0.5 and high can never exceed it. Low and high both crowd toward 0.5, and the midpoint of 0.5 and 0.5 is just 0.5. The guess becomes itself. There is a second culprit hiding here, floating point. In a step-by-step tracer, the early passes behave, nudging low and high correctly, but values that should creep past 0.5, like 0.499, eventually round to exactly 0.5. Recall that 0.5 is 1/2, a clean power of 2, so the computer stores it perfectly. Once a value lands on 0.5, rounding can no longer budge it. With infinite precision, you would approach 0.5 forever. In real arithmetic, you arrive and stay. So how do we fix it? The loop logic is perfect. The bug is only where we start and end. For x between 0 and 1, the answer lies somewhere above x. The lowest it could be is x itself, and the highest it could be is 1, because the square root of any fraction below 1 is still below 1. So set low to x and high to 1. Same code, new endpoints, and the search now brackets the answer. To handle any input the user throws at us, we guard the endpoints with one if-else at the top. If x is greater than or equal to 1, the square root sits between 0 and x, so low is 0 and high is x. Otherwise, if x is greater than 0 but less than 1, the square root sits between x and 1, so low is x and high is 1. We require greater than 0, so a negative input doesn't slip through. Everything below this guard stays exactly the same. Here's a reassuring detail. Suppose for 0.5, you lazily left low at 0 and only set high to 1. It still finds the right answer. With a tight interval from 0.5 to 1, the search settles on about 0.703. With a loose interval from 0 to 1, the first guess is the midpoint 0.5, which is x itself. The loop spends one extra pass climbing past it, and then settles on the very same 0.703. One extra guess is nothing to a computer. That is the whole power of bisection. A sloppy start costs almost nothing. Step back and compare bisection with the old approximation method. Two things stand out. First, bisection reaches the answer in dramatically fewer steps, and the answer it gives is every bit as good, just as close to the true square root. Second, the early guesses do far more work than the later ones. The first cut is the most dramatic, and each cut after that matters a little less. Recall the book search example. The first guess threw away 200 pages in one stroke. The second eliminated only 100, the third only 50, and near the end we were trimming about 4 pages, then 2 at a time. The drama fades as you close in. That is logarithmic growth. Each step halves what remains, so the absolute amount you cut shrinks even as the search marches steadily toward the answer. Bisection is powerful, but it isn't always available. It needs 3 things. Your search space must have endpoints, a definite low and high to bracket. It must be ordered, sorted by number, by letter, by anything consistent. And every guess must give feedback, telling you whether it overshot or undershot. Take away endpoints, order, or feedback, and bisection has nothing to bite on. No halving is possible. Now your turn, adapt it as a worst example. Find the cube root of a positive cube using bisection. The setup is given. The cube is 27, the tolerance epsilon is 0.01. So the guess cubed must land within 0.01 of 27. Start with low at 0 and high at the cube. We'll build the rest together, the inside of the loop first. Start with a while loop. First define the guess as high plus low divided by 2, the midpoint. The loop runs while the absolute value of guess cubed minus the cube is greater than or equal to epsilon, meaning we are still too far off. Why not stop when that distance is exactly epsilon? Because comparing floats for equality almost never hits exactly. Picture the target with epsilon as a band around it. You keep guessing while the distance is bigger than that band, and you stop the instant you're inside it. Now the inside of the loop, decide if the guess is too high or too low. If the guess cubed is greater than the cube, the guess is too high, so high becomes the guess. Anything bigger we discard. Otherwise, the guess is too low, so low becomes the guess. Are we done? Not yet. We must recompute the guess as the new midpoint, high plus low over 2, or the loop never moves. Finally, outside the loop, print the guess. Running it gives 3.0009, not exactly 3, because we stop the moment we're within epsilon of 27. So the same powerful loop solves square roots and the cube roots alike. The logic never changed, only the endpoints and the test did. The real lesson is sharper. When a search loop hangs, suspect your interval before your logic. Make sure the answer you seek actually lives between your low and your high. To practice what you just learned, this course has free exercises and AI-graded feedback on ludium.ai. The link is in the description.